Today we will talk about Biot-Savart's law. It is one of the important law in magnetism. So what it states? So it states that actually suppose let us assume that there is a current carrying conductor. So it is carrying a current of I amperes. Okay. So it is carrying a current of I amperes, and this is the conductor. Now you can see this conductor is going like this. Now let us assume that consider a point. Let's say the point is P. So at P, what is the magnetic field intensity? So this magnetic field intensity at P is given as H. So what is the total magnetic field intensity? So this can be easily calculated by using Biot-Savart's law. So due to, let us consider a small a current element. Let us see, this is a small element, let's say a differential length dl, and note that this differential length is a vector quantity. So this is a vector quantity. Okay, it is having a direction also. So this is having the differential, this is the differential length dl. Okay, and this is the direction of this. Okay, now in this case, due to this current element differential of differential length dl, we can have a small magnetic field due to this as dh at the point P. So how it is related to the current and the differential length dl? And let us consider the distance from the differential length, to the point P. Let's say it is nothing but some r. So before that, we will consider the vector which is pointing from the differential length to the point P is given as r, the vector r, and the magnitude of this is given as magnitude of vector r. So this is giving you the magnitude, okay, and this is the vector, okay, the length of the vector is given as magnitude of r. Now it is found that the differential magnetic field intensity is proportional to the current, okay, and it is also found that the differential magnetic field is proportional to the current element dl, okay, this is proportional to the dl, okay, and the differential length dl, and also it is inversely proportional to the square of the distance. So what is the distance? It is the magnitude of r square. And also it is found that, let us assume that this is the angle between the differential between the current carrying line and the vector r. Okay, you can take the angle in some textbooks. You can see that they have taken the angle here also, alpha. There is no issue, both will give you the same answer. So it is found that the dh is proportional to the sine of this angle alpha. Okay, so we can combine these results. So what we will be getting here as dh is proportional to I, okay, then dl, okay, then it is inversely proportional to the distance magnitude, that means r square. So we can introduce the proportionality constant as 1 by 4 pi, and there is one more thing, dh is proportional to sine alpha, so it is also proportional to sine alpha. Now what is the direction? What is the direction of this magnetic field? So this can be given by using the right hand thumb rule. So let us see here. Actually you can see this is my thumb, and my thumb will be pointing the direction of the current, and you fold your fingers, other fingers, then that will give you the direction of the magnetic field. So here you see, if you see here, so I am going to remove this part anyway. If you see here, the current is moving in this direction, so I will hold my finger in that direction. Now you fold your other fingers, you can see that it is going into the screen. So it is going into the screen. So I will be showing like this. So on the right side, you can see here it is going into the scene, into the screen. So I will draw in a different way here now. So it is going into the screen, and if you point your other fingers, you can see that the other fingers will be coming out on the left side. So it will be coming out on the left side. So you can see here that it will be going into the screen. So this will be the magnetic field. So it is going into the screen, and on the left side it is coming out of the screen, and this is the magnetic field due to this current carrying wire, and the current carrying wire is carrying the current in this direction. Okay, so this is what the magnetic field. Now you can see here that we want to represent this direction. So let us consider how we can represent this direction. So that is the main question. So you can see we have seen that I, and we have seen the differential length dl, and we are going to calculate at the point P what is the magnetic field. We see that it is going inside at point P. So the dH at point P is given as, and this is the vector r which is joining from dl to P. Then the magnitude of vector r is shown like this. So dH is equal to 1 by 4 pi, okay, 1 by 4 pi, then I dl sine alpha. What is alpha? Alpha is the angle, so divided by, and it is inversely proportional to the distance, magnitude of r, the whole square. Now you can see there is a term which is known as sine alpha. What is this sine alpha? So let us consider the unit vector in the direction, your unit vector in this direction. That means unit vector in the direction of r is AR, and the unit vector in the direction of DL is given as AL. Okay. So what is AR now? What is AR? We know that AR is equal to vector R divided by the magnitude of vector R. Now you see the direction of the magnetic field, that is, it is going inside, and there is also sine alpha term. So we can beautifully represent this concept by using the cross product. So I will represent it in cross product form, that is 1 by 4 pi, dH is equal to 1 by 4 pi I, then I need dl into sine alpha. I can represent this dl into sine alpha as dl into dl, okay, sine alpha as dl cross AR, okay, because dl cross AR is equal to dl dl, okay, the magnitude of dl, okay, so the magnitude of dl into AR, okay, AR, what is the magnitude of AR? Magnitude of AR into sine alpha, and you know that the magnitude of AR is equal to 1, and the magnitude of dl, we can say it is dl. So before that, it is best to represent this dl as a vector, as I shown you. So this vector, I can show dl as a vector. So I will use this notation here now, dl as a vector. So dl as a vector. So it's better to show the dl as a vector. So it is found that dH is proportional to the magnitude of dl. So I can represent this magnitude of dl here. So what is the magnitude of dl? Magnitude of dl is, I will represent as dl, okay. So the magnitude of dl, I will use the notation as dl. Now I can show this as 1 by 4 pi I into the vector dl cross AR divided by magnitude of R, the whole square. But you know the vector AR is given as the vector R over the magnitude of vector R. So in general, I can represent my dH as 1 by 4 pi I is the current, then the vector dl, okay, vector dl, the vector dl cross magnitude of, the vector R over the magnitude of vector R, then already there is magnitude of vector R, the whole square is there. So I can get my dH is equal to 1 over 4 pi I dl cross r, okay, divided by the magnitude of r the whole cube. So this is the equation for the magnetic field intensity due to the small current element dl. So let us consider this is small current element dl. So it is having a direction I am showing. Actually this is the direction of the current I. So I can say that the direction of dl, so this is my vector dl, I can represent it as dl into al. So what do you mean by al? Al is the direction of dl, okay. Al is the direction of dl. So this is what we have seen, okay. So the magnitude of dl bar is dl, okay. So this is the direction of dl. So I hope it is clear to you. So mainly you have to just remember two things. Suppose there is a current carrying wire. If there is a current carrying wire which is carrying a current in this direction, you see this direction we will call actually the length, the direction of the length, and you want to find suppose the magnetic field here, let's say the magnetic field here at P, then you will see this is R, okay, and this is your R. Now you can actually get the direction as AL cross AR, that is the direction, or we can say it is DL cross R. So this is the Biot-Savart's law. I hope this is clear to you.